So, Roberto, the stage is yours.
Okay, well, thank you. Let me take it from where I left it yesterday. So I finished the lecture with this example because we saw how generalized complex structures could be seen not just as these endomorphisms of Tm plus T star m, which are skew-symmetric and square root minus the identity. There were also these subbundles that are maximally isotropic and involutive. That's a complex Dirac structure and have this extra condition of L intersection L bar equals 0. And then mainly the main thing yesterday was to see how these locally, it could be expressed as some differential form, satisfying some extra hypothesis. Actually, I needed one hypothesis for every condition I have. So in order to understand this properly, the best is to have an example, an interesting example. And the best is the one I suggested you to look at, which is C2 with coordinates ZW and this differential form. To start with, we've been doing things on real manifolds. So when I wrote C2, the first part of the problem, if you want, was to understand that, okay, when I write C2, I'm actually referring to R4, okay, and that here, if I have coordinates, say, X, Y, U, T, so that my coordinates in the C2 are going to be just, so the usual thing, okay? This, of course, it's very easy, but I just want to make the point that actually when you replace this into there is when you can really see that this phi is actually a complex form on R4, okay? So this is the object I'm talking about. So now we want to check the three properties that will make this a generalized complex structure, okay? The first one is to be pure, okay? That actually for L to be maximally isotropic, what I needed was pure spinor, okay? And I described how pure spinors are. And here, because of how it is, this phi that it changes, it's minimum non-zero component, I'll have to distinguish two cases. So I have to do when z equals 0, my phi is just this thing here, okay? So if you remember, pure spinors were something like e to the b plus I omega, and then I had some decomposable form here, okay? And here I'm also taking the wedge product down there. So, okay, this actually fits perfectly because of those terms there, okay? So that's pure. And what happens when z is not 0? So when z is not 0, remember that the structure that gives spinor is the same as the structure given by a function times the spinor, okay, when f is non-vanishing, okay? So when I am assuming that z is not 0, what I can do is actually write, instead of writing this phi, I can write phi over z, okay? This is giving me the same structure, and this is actually 1 plus dz wedge dw over z, and this is actually e to the dz wedge. Why is this? Okay, because this exponential is 1 plus the form plus the square of the form, but this square is going to vanish because I have repeating terms. So it's actually this exponential. And of course, this is a complex form. So here I separated my real and my imaginary parts, because as I mentioned, real two forms, when they are closed, they are actually symmetries of my theory. So I'm left with the omega, which is a symplectic structure, okay? Here I'm writing all together, but for now, I mean, it doesn't matter. This is some b plus I omega that you can actually compute. It's just computing the real and the imaginary parts, okay? So actually, this is a pure spinor. Second condition, let me go for the one we had in the Dirac structure, was to say that I have this condition. So this was rewritten as having this thing for the pairing. Okay, this is what I have to check now for this phi. Okay, so yeah, I just have to do it. So I just have to compute the pairing of this thing here and the conjugate. Okay, what's that? It has to be a top form. Okay, and we are on R4. So top forms, okay, are going to be 4-dimensional. And because I'm R4 complexified. So I'm only this, by the way, I'm missing the T here. Yeah. Okay. Sorry, no, I'm not missing the T yet. This is the pairing. This is the pairing, and the pairing is what it is the top component of this thing here. Here I take the transpose, which here I just take the same thing. And here I take the top component. Okay, but I mean the transpose here is just going to change the sign to actually, or just to transpose actually. It will just say dw dz. And the top form, top here is 4. So I'm left with this thing with dw dz dz bar, which is not equal to 0. So this, okay, satisfies the condition that will give me that the annihilator of this form satisfies L wedge L bar equals 0. Last condition, and it's the last one because it has to do with integrability. So remember, in the case of L, it was L involutive, and L involutive is actually equivalent to having that the differential of the form equals some V acting on phi for some V, which is a section of Tm plus T star M. In general complexified, you can actually reduce this to real, but it's okay for us. It's better for us to do it like this. The example we saw before, D of the spinor for a symplectic structure or D of the spinor for a complex structure, they just vanished. Okay, so it was very similar to a symplectic form being closed, say. But this is very interesting, this example, because you have D of something that's not going to vanish. Okay, because this is dz. It's not going to vanish, but I can get to it by acting with a generalized vector field on the same spinor. And in this case, because I observe that the term dz appears here, what I have to do is to kill the dw. Okay, so to kill the dw, what I have to do is I act with minus, okay, this one here, because, and plus the zero form, acting on z plus the omega. Okay, so yeah, this kills the z, and then it gives me precisely the z. So it is a generalized complex structure, and it is a very interesting one because, as I said yesterday, what's happening is the following. In C2, which I will just make a views here of, imagine this is C2, okay? So in z equals 0, my structure is like dz, which the omega, but this is actually the usual complex structure of C2. This is the way I see a complex structure when I see it as a form, okay? I see it as this 2-0 form, because it's just a 2-0 form. Remember, I changed the sign conveniently so that, yeah, I put minus j and j dual, so that here I get a nice 2-0 form. And what do I get when z is not equal to 0? So I'm getting this structure, which is e to the dz wedge d omega over z. And this I said, okay, this is e of some real part, some imaginary part, and this is EB, I omega. Okay, this is something you can check with the wedge product. But this is a symmetry of my theory, and this is a symplectic structure. So this is like taking a symplectic structure and applying a diffeomorphism, but a generalized diffeomorphism. Okay, so this is a very interesting phenomenon of generalized complex structures, which is type change. Okay, so now let me, before I come back to the type, let me say something that I think it's quite important to understand to grab this complexity of why local, because of course, I mean, what I'm saying at the end of the day is I have my manifold. Okay, if you think about it, if I have my manifold, and then you are telling me, look, you can put subspace subbundles L, okay, of Tn plus T star, and this would be my structure, okay, some L inside Tn plus T star n complexified all over my manifold. This is a generalized complex structure when it satisfies the right properties. Or what I'm saying is you can actually take a local place, and in that open set you define some differential form there, okay, this phi u, say, for some open set, and this is, I'm going to write it like this, a complex form in U, okay, such that the annihilator of this thing is actually L restricted to U. And if you take a different one, so you'll get some phi v, which will be something here, and the same, the annihilator of phi v equals L restricted to V. And what has to happen in the intersection? So in the intersection, there is something quite remarkable, which is like for pure spinors, because these two are pure spinors, the annihilators are the same, okay, if and only if one is a multiple of the other. Okay, we had one direction before. It is clear that if one is a multiple of the other, then the annihilators are the same. But you can also check that actually if the annihilators are the same, the only way they can be the same is because they differ by a non-vanishing function. Okay, so here, as usual, this non-vanishing. So what I'm saying, I'm making this point because, okay, look, this phi and this phi u and phi v may not be the same, but they only differ by a constant. Okay, so well, why don't you just multiply your phi v by a constant? Okay, imagine like you have that this phi v equals f times phi u. So you say what? So instead of considering phi u, just consider f times phi u. Okay, so replace, if we replace phi u by f phi u, then I could define phi in the union of these two, because I'm just making them agree on the intersection. Okay, and you can think, okay, why don't you go do this, what will be the issue? Okay, so I'm going to show you what's the issue with an example that actually goes beyond the interest in generalized geometry. It has to do more with complex geometry. Okay, so think about S2. S2, as any orientable surface, has a complex structure, and in this case, the best way to understand the complex structure is just by seeing S2 as the complex numbers and just a point in infinity. Okay, this is very easy because you take S2 and then your infinity is the North Pole, and then you do the stereographic projection to the plane, and this is giving you, okay, this correspondence here. So this is a manifold, and you can give complex charts for this manifold that are very nice. So you take two charts. So one chart goes from C to C and gives you just Z to Z. And the other chart goes from C minus 0 with infinity. Okay, now I'm leaving somehow of the South Pole, and it goes also to C. And what it does is sends Z to 1 over Z. Okay, so these are the two charts. They are complex charts, and you can see what's the change of chart. And the change of chart is the map that goes from C minus 0, C minus 0, because it's just the intersection, to 1 over Z. Okay, so this is holomorphic. So these are a complex chart. Okay, how would I express now this complex structure on C union infinity with differential forms? Now I've given the stronger thing, which are just the complex charts, okay? But if I want to express this complex structure, what I will have to define are these, in this case, 1-0 forms, okay? So say here that on C, okay, like recall that on C, the complex structure is given by dz. Okay, this is the form that if you take the annihilator, okay, you get this, this case 0, 1 vectors. Okay, and we know the 0, 1 vectors determine the structure. Here, I mean, it may seem a bit tautological because we are on C. Okay, it's but you could do it with C to some power. Okay, but for us, it's better just to stick to the sphere. Okay, and what I'm saying is, on C, the complex structure is given by dz. So look, on the sphere, except the North Pole, okay, just on S2 minus the North Pole, if I define dz, that is giving me a complex structure everywhere but at a point. How do I complete this complex structure to the whole thing? Because it does have a complex structure, okay? So I look at the other chart, but when I look at the other chart, okay, the other chart, and now I'm missing here the South Pole, the other chart is actually the map that goes from C to my manifold, this one here, is 1 over Z, okay? So the way I have to define here the complex structure is actually this differential form, which is minus dz z squared, okay? So on the complex sphere minus the North Pole, okay, on the sphere minus the North Pole, I define the structure as dz. Whereas in the sphere minus 0, but with infinity, okay, here I'm taking away 0, and here I have infinity, I'm taking infinity, my differential form, okay, sorry, and in here I'm not, okay, this is in the intersection, sorry, okay, this actually, because this is not well defined in plus infinity, so actually what I'm writing here is in the intersection, for this to be well defined. Intersection, okay, there is a well-defined form on the sphere minus the 0, but I won't be able to express it so easily. So let me just look at what that form is in the intersection. Okay, so in the intersection, which is the sphere minus North and South poles, the complex structure given by this chart is actually minus dz over z squared. Okay, this is well defined. Because I'm not considering 0, I'm not considering infinity, okay? And what I'm saying is that actually this kind of extends nicely when you have the infinity there. And on the other hand, I have another differential form dz. So these two things are not the same, okay, on the intersection, but they differ by a function, which is non-vanishing on the intersection as well, which is 1 minus 1 over z squared. Okay, so here, okay, there is no global form, and we can see why somehow, because dz I can extend it to infinity, and this thing here I cannot extend it to 0, okay? But still I have one form which is well defined on one side, one form which is well defined in the other, and in the intersection they are related by a non-zero function, okay? So somehow here I can say dz on C. Now I'm going to put between quotes this thing, but okay, this thing on Z minus 0 union infinity. And in the intersection, okay, I have actually dz versus minus dz z square, okay, because this is what it is. Okay, so I can see how I won't be able to get a global one form, but still the complex structure is well defined, okay, because I have these local 1-0 forms giving me the same complex structure because they differ by a function. Okay, so having clarified this about this importance of locality, let me wrap up what I had to say for complex, for generalized complex structures. Let me see if this moves. Okay, here it goes. So I wanted now to summarize what this type is doing for me. So the type, as I define it, is an invariant of this structure, and it takes some values which are from 0 to m, where n equals to m, 0 is complex, and m is 0 is symplectic, and then m is complex. This is complex, and this is symplectic. So the interesting thing is that I've shown an example where the structure is almost everywhere symplectic, but at some point it jumps to complex. So generalized complex geometry has this power of, on your manifold, okay, you can have some open set there, and then you may be of one type, and then all of a sudden you can jump. So there is actually a property, type is upper semi-continuous. So you can actually study what are the properties of these jumps, of this type change, okay? It has to be an upper semi-continuous function. Why? Because how functions vanish, okay? Remember, the type is just the first non-zero vanishing component, okay? So it has to vanish on something closed, say, okay? Actually, it has, usually if it's non-degenerate, it has codimension 2. You can describe it very well. And apart from being upper semi-continuous, you also know that the jumps are by 2, okay? And this is a property that comes from pure spinors. And in any case, it doesn't matter how much complex structures are jumping, we can look at their geometry, what happened locally, okay? And there is an interesting fact that I was hiding so far, which is, notice that when you have any J like this that has some components, if you look at this part here, which is just the projection to Tm of J restricted to T star M, so this is actually a bivector, okay? And it turns out that this bivector is a Poisson structure. So any generalized complex structure has a Poisson structure on it, and it gives you a symplectic foliation. This, I recalled it when I talk about the presymplectic foliation of Dirac structures. There is a theorem by Bailey saying actually how do these structures look like, and any generalized complex structure locally will determine a symplectic foliation which is the foliation coming from this Poisson structure with, and now it's something, okay, a transverse, and I'm not going to stop here, okay, but just let me say the name, holomorphic Poisson structure, okay? So this is like an enhanced version of like, combining complex and Poisson, okay? It's important, the holomorphic, because actually in most of the points, in the regular points, what's going to happen is that you are going to have the symplectic foliation and you are going to have a complex structure on the transversely, okay, on the space of leaves. So say, in regular, where there is no type change. So generalized complex structures, they look like these symplectic leaves. And the idea is that transversely, like if you take a slice, this section, that's going to have a complex structure, okay? What happens in general when the type changes is that this is not anymore a complex structure. It will be some point there where things will go wrong, okay? Like, and then you have these holomorphic Poisson structures. So this is the local description of the object, so the geometric description of the object we have dealing with. I think it's time now to say why we are doing all this, okay? So why generalized geometry? And there are three reasons I would like to give briefly, okay? The first one is like, it gives us a common framework for the structures that before were disconnected, say complex and symplectic, okay? So people who were doing mirror symmetry and they were wondering why sometimes the mirror of a complex is symplectic or a symplectic a complex, why are they mixing? Okay, now they are the same. They're all generalized complex structures, okay? So in this sense, this offers you this common framework. On the other hand, it's a very convenient language, okay? And for instance, I said yesterday, I mentioned this example of extended deformations. I would like to give something simpler today, just to refer to the analog of Keller structures. So you can talk about generalized Keller structures, and this comes from Gualtieri, like 2003 when his thesis, and he realized actually these structures were the same as some structures that were defined before in the physics literature called by Hermitian in the 80s. And they were defined, they were studied in a few papers, but they were not pursued because they didn't have the right language probably. Okay, what happened when generalized geometry was introduced, if you look at how many papers cited by Hermitian geometry, you will see that, okay, it starts like this, and when generalized Keller geometry appears, all of a sudden there is a lot of interest because there is the language to say things about them, okay? Then of course, I mean, it has a lot of a trend. Of course, then it goes down and okay, now I don't know where it is, okay? But it's a good example of this convenient language. And the third one, that is the one I like most, is genuinely new structures, okay? So, why? Because I have this type change. So now I can describe structures that were not there before, okay? And not only because this, of course, it can be very naive to say, okay, yeah, you are mixing these two things. Of course, it's a new structure, but okay, it's very close to complex because any generalized complex is almost complex. And yeah, the thing is that you also get, with these new structures, you get new classes of manifolds. Let me use the example with which we started today to tell you how they can do that. Okay, you remember we had this z plus dz wedge d omega, and this was defined on C2. Now look, like the W, it doesn't appear in the zero term. So it's invariant by translations. So if it's invariant by translations, okay, this W invariant by any translations I do. So I could actually define this on C times C, yeah, and the translation by Z2. And this is just a torus, okay? And here I can take actually a disk inside of C. So what I'm saying is that I can produce some object which is like a torus and like a thick torus, like I multiply by the disk in such a way that the nerve of this, okay, the nerve is kind of complex, okay, is well type M, okay, and the rest is symplectic. So it turns out that there is a construction where you start with a 4-manifold, okay, which is symplectic. It has to be a very precise one, okay? You just take a torus here that has a trivial normal bundle. You take a thick, okay, you take a tubular neighborhood of it, and now you take it out and you put this one inside. And if you do it carefully, you can do it in such a way that you still get a smooth manifold, of course, but also that you get a generalized complex structure on this manifold, okay? So by doing this process, we are introducing type change in some 4-manifold. And the surprising fact is that it can be done in such a way for some specific choice of M4 that the result of this process is actually, you can say what it is. It's 3 CP2, 19 CP2s, this. And this manifold is generalized complex, but is neither complex nor symplectic because it can be proved by Seiberg-Witten invariance, okay? So what this is telling you is that, okay, you have the world of almost complex structures. Inside of them, you have complex structures. Where do generalized complex structures live? They live somewhere here because I know there is an example, this manifold here, which is not complex. Okay, and this is very interesting. And if you ask me for more examples, I won't be able to give you any other examples which are not in dimension 4. Why? Because it is still an open problem to know whether there are manifolds in here for dimension 6 or greater. That's an open problem. We don't know it yet. Okay, so generalized complex is there in the middle in dimension 4. Could it be in the middle in dimension 6? That would mean that actually complex and almost complex is not the same for 6 or greater, okay? So it could play a role in that problem. Of course, that's a very difficult problem. So yeah, I can't even forecast whether that will be the case. Okay, so having said this about the wide generalized complex structures, wide generalized geometry. Now, let me finish by taking you on a trip to complex Dirac structures, okay? Look what we did is we have this type that in generalized complex structures was telling me how structures are changing, and it was nice to have now these structures changing, okay? This is actually the work of the thesis of Dan Agüero, which was co-supervised by myself and Enrique Burstein. So why all of a sudden complex Dirac structures may have interest? I was before saying, okay, no, we need this condition L intersection L bar equals 0. Okay, but when you, for instance, want to look at some manifolds, so something similar to what happened with symplectic structures, you look at as a manifold, that's a pre-symplectic structure. When you look at some manifolds of generalized complex manifolds, so they are not generalized complex anymore. Okay, if I have here just this as a manifold, and I have some generalized complex structure, which I will write just like this, Lm generalized complex. And now I do the pullback of this. So this pullback to n, actually you can see it's complex Dirac, but of course it's not going to satisfy the condition of the L intersection L bar equals 0. Okay, so it makes sense to study complex Dirac structures, and actually it's a simpler definition. I'm going to recall it. That generalized complex structures. Complex Dirac structures are just maximally isotropic plus involutive L inside Tm plus T star M. See, okay? So what I would like to do very shortly is to tell you what are they? In the same sense that for Dirac structures, I told you, look, Dirac structures at the end of the day, they are presymplectic foliations. Now, for generalized complex, I told you, okay, they are very flexible structures where you can change your type. You're symplectic, and then all of a sudden you have something that looks like complex. Okay, and essentially they are like these symplectic foliations with some transverse complex, or in general holomorphic Poisson structures. Okay, and the invariant there was the type, and the type was like a segment. Okay, that from 0 to m was actually only the integers and with some rules. Okay, so I would like to do the same with complex Dirac structures. To start with, there is something, some invariant is on our face, which is an invariant that will tell me when a complex Dirac structure is actually a generalized complex structure, and this is the real index. So the real index is just the rank of L intersection L bar. Okay, this is a function. It depends on the point, may change. Okay, this is telling me when it vanishes, I know I have a generalized complex structure. Okay, so it makes sense if I want to study complex Dirac structures to look at what's the real index. Okay, and then I will start to know something. So on the other hand, we know that any L, okay, because are maximally isotropic, L is L E epsilon. Okay, there is a reason why I insisted in doing this proof, is that we are using it everywhere. Okay, and now the thing, this E is actually not even a subbundle, okay, it's a distribution, it may change its rank. It's something complex, and this thing is also complex. And you know, a complex subspace, you can't understand it geometrically. When it was a real subspace in Dirac structures, we managed to see it as the tangent space to a leaf. But what am I going to do with a complex subspace? Okay, I'm not going to complexify my manifold. So the way to deal with this complex thing is to define something real out of them. So you can define two new distributions, D, which is just like the real part of the sum of this thing. Look, I'm just taking here the sum with the conjugate to make it real, for this to be the complexification of something. So these are real objects, okay, and they actually determine my they will determine my E later. Okay, so these now are real, so I can make sense of them. And what happens, and now I'm just telling you the story, okay, I'm not proving things, is that the epsilon is actually making this delta presymplectic, okay? Whereas the E, even the same subspace, is actually doing D over delta complex, okay? So what's happening is somehow I'm determining on my manifold, I'm determining some leaves that are presymplectic. So now you can see already how this generalizes generalized complex structures, because before I had symplectic leaves. Now I say, no, this complex Dirac in general will give you presymplectic leaves. And what do I have transversally? Okay, so transversally, I do have this, that D over delta, which is something which is inside Tm over delta, that this is complex. And when something is complex and it is a subspace, this is actually what's called a CR structure. So this is the other way complex Dirac structures generalize complex structures. Okay, symplectic becomes presymplectic, and the transverse holomorphic or holomorphic Poisson, okay, will have this CR character. Okay, there will be something complex, but it will be just a subspace. Okay, so how do I describe in the simplest way, or try to make sense of how much complex or how much presymplectic, how do I weigh this? Okay, before the type was weighing how much symplectic and how much complex did I have. So now I have the real index to help me, but I need some invariants to say how presymplectic or CR are things. Okay, so the new invariants, the convenient ones, are something called order, which is just the co-rank of this distribution D, which is actually telling me, okay, like the CR, how far it is from being complex. And actually the type, I have to redefine the type. Okay, this is a new type. It coincides with the previous one, but what I do here is to say, okay, the type was telling me how complex something was. So, okay, so I just do this thing. I'm telling how complex it is, okay? Because this, I said, it's complex, so I'm measuring how much that is, okay? So now, look, we have these invariants. You can prove some relation between them. I'm not going to enter there now. Real index, more like bounds, okay? In the same sense the type was bound. And it happens that for generalized complex, the real index, you know, it's 0. It happens that the order is bound by the real index, so this is 0, and the type was just taking values between 0 and n. Okay, good. What does it happen for complex Dirac structures? So think about it. If I had one invariant, I had a segment. Okay, but now I have 3 invariants, so I can see for each of the value they are taking, what type of a structure am I getting up to generalized diffeomorphism? That's quite a leap, because from a segment, now I can go to a 3-dimensional figure, okay? So actually, I prepared it here. Oops. See that this. So this is the analog of that segment for generalized complex structures is this right tetrahedron for complex Dirac structures, okay? So look, this is the segment, symplectic, generalized complex, that's the segment I had before. This is all I had before. And now all of a sudden, because of these new invariants, you can see it here, okay, the type is that direction. Now I have more real index, I can turn the things that were symplectic into presymplectic, okay? I have this thing of presymplectic leaves, okay? I have the things that were complex, I can turn them into CR, and I can combine them, okay? And actually, combining Poisson and presymplectic is Dirac. Those were the 2 extreme cases of Dirac, okay? And now I have a whole new universe of structures here. And at the very end, what I have are just, I mean, I can look at Dirac in 2 different ways even, okay? There is like just the complexification of the structure, or there is some structure associated to a Dirac in a different way here. But the interesting thing is, in the same way, before I could be symplectic and then all of a sudden jump here or jump to complex. Now I can move in 3 directions, okay? So I can actually go from here to there and then there, and of course there are some rules, okay? Depending on how this function, they have to be upper semi-continuous, sometimes they have to jump by 2, okay? But I have a whole new universe of structures. So this is actually giving me a more general framework in which I can understand many geometric structures. This is a picture which is like kind of the easy way to remember it. Let me show you like what really is something more like this. Okay, so this is this right tetrahedron. You see, because okay, it's right because here, for instance, I put here that the real index is up to 8, okay, and the order is as much as the real index. This is why I have these lines here, like, and the type is half. Okay, here actually the dimension is 8. Let's put it this way: the dimension is 8. The real index goes from 0 to 8. Order from 0 to real index. This is why I get this triangle here, and then type is 4. Okay, and then okay, this is my structure. So this is the view you were saying, and I have to add something. You remember I told you just today, I know, but I told you that you can associate to every generalized complex structure a Poisson structure. So to every complex Dirac structure, you can associate a generalization of a Poisson structure. And what are those? We saw it the first day. Those are Dirac structures. And how does that happen is in a very geometrical way, actually. I also just told you that this segment at the back are Dirac structures, are complexifications of Dirac structures. So actually, I can see that there are planes of structures here, okay? So here I'm taking planes on this tetrahedron, and what I'm saying is all the points lying on these planes, they all go to a Dirac structure that is lying in that segment there, okay? So I can see it geometrically in a very nice way. Okay. So this is essentially where I wanted to arrive. Let me just add a couple of things. So to start with, you can contact me if you have any question, given that I wasn't able to go personally, and I would have loved to speak to you personally. So you can.
Roberto?
Yes.
We don't see your chat
Ah,
screen.
you don't? Yeah. Thank you. Yeah, it's true because I just removed the. Yeah, I was just writing. Okay, now I'm sharing now the whiteboard. Yes. Okay, so ub.edu, or you can just also write to my personal email, roberto.rubio, and then you add Nunes there at gmail.com. So I'm available if you have some question, given that the interaction, you know, it's not so easy online. So yeah, I'm sending you the, because yeah, someone asked for them, so I will share with you also these notes. The thing is, I'm also now in this project of writing an introductory book for this, so I will be very happy also to share that with someone who's interested. And what I'm doing lately with this thing, and let me show you in case someone is interested in really knowing, like learning a bit more about this, for the sake of generalized geometry, or for the sake of geometry itself, okay, because it contains, it relates to many other topics, is I'm putting the notes on this platform called Perusal, and then when I have a group of people, interested people, so this is like a bit of a social network to learn math. It sounds a bit geeky, but it's quite convenient. So people just highlight things, and then we comment and we answer each other. So you can go to some discussions and you can see how some people write comments, and then they upvote. And in this is a nice way to just have a text and read it together, even if we are not together. Okay, so if anyone is interested, just drop me an email, and whenever I open a new group for this, I can include you. Having said that, let me just finish by thanking the local organizers, Cedric, Xavier and Jordi, and especially all of you for your interest. And I hope next time we'll be able to see each other face to face. Thank you very much.
Thank you very much. Thanks a lot, Roberto, for this nice mini course that you gave. So, other questions? Maybe I have one. It's a very basic question, but I didn't get like this last. Well, I mean, before you talked about. So the example that you talked about, which is not symplectic, not complex, but it's generalized complex. So this construction that you did, where you, if you can go back to your slides, I don't know if you can.
Yes, I will do that.
So I didn't get this result because you don't change the topology of the manifold doing this gluing argument that you do here, or do you? I mean, I don't understand how you get 3 times CP.
Well, I mean, you start, you change the topology of the manifold, yes. Oh. Because this is like some kind of K3 complex surface, something. It's a kind of vibration, like it's a vibration of a K3 complex surface, and then you will get to. You are changing. I mean, your manifold to start with is symplectic, okay?
Okay.
And then you end up with something which is neither complex nor symplectic. So you remove the torus there, okay, and you are going to glue the other one in a special way. This I didn't do it. This is actually, I should put here. Yeah, I was reviewing some things of other people. Of course, this is due to Gualtieri and Cavalcanti, but actually they were taking advantage of something called, I think, C infinity log transformations, and so essentially this process was there before they had to adapt it to this case. Okay, so you do change. I mean, this M4 and the result is very different. I think it may be also the way, a torus you can glue it in different ways. Okay, like these then feelings as well. So now I don't know it from the top of my head, but yeah, you do change the topology, and you are able to prove that the resulting manifold is neither complex nor symplectic. But okay, you've done it in such a way that it is still generalized complex.
So it's symplectic just away from the core of that torus that you glue in, or?
Yes, yeah, of course. It's going to be generally symplectic, and then it's unfair, by the way you think about it, to say at this point it's complex. What does it mean to be complex just as a manifold? No, it's a generalized complex of complex type, okay? Because I don't have a neighborhood where it is complex. No. Okay, the change of type happens in something that has some codimension. In this case, I have dimension 4. So remember, the type was the first non-vanishing component. Okay, so here I'm just looking at the degree 0 component, the non-vanishing of a complex function. It gives me 2. 0, so that's why it reduces the dimension into 2. Okay, so it's you are cutting by these 2 constraints. So you have some codimension 2. In this case, you have a torus inside, okay, which will be the one in the middle, which is not fair to say, okay, complex, okay, it's generalized complex of complex type. Okay, it looks like the exact thing to say is that it looks like the example I showed you before, because actually the example I showed you before is how all non-degenerate generalized complex structures look like, okay? Which these are the ones that are stable. They are called stable generalized complex structures look like. They are all like that, okay? And this is what you have in this neighborhood. So again, it's symplectic generically, but there is something there, codimension 2, where the symplectic goes in some way that you cannot make it symplectic anymore, that you can make it generalized complex, okay?
Is this like, I mean, is this what is called in the literature elliptic symplectic, or well, now I don't remember exactly the name, but I think there's, maybe I'm wrong, like.
Well, as far as I know, I mean, this is, in this generality is just generalized complex. It's true that then, okay, then there is, I mean, there are these other approaches like, okay, log symplectic and bisymplectic that you know better than me, okay? That somehow go in a similar direction, yeah.
Okay.
But in this case, I mean, for manifold, I tell you here, it's as simple as that. You know what's happening in a neighborhood of here is just the model I gave you. I mean, you don't even need some more. I mean, it's good to have a more general theory, but around that torus, there what's happening is z plus dz wedge dw. That's all that's happening.
Okay. Okay. Thanks a lot, Roberto. So, are there other questions? Yeah, there's another question here.
Hi.
Hi.
I was wondering if there is any relationship with generalized geometry with geometric quantization, in which we need a polarization of tangent bundle. No? So I was wondering if there is some relationship using the language of generalized geometry.
Can you repeat? You said to any relation to geometric quantization?
Yeah. I was wondering if there is some relationship with this field.
Yeah, I now from the top of my head, yeah, I have to let me just see if I from the top of my head I can tell you like of I'm refreshing, yeah. I can't even see when you put generalized geometry quantization, nothing appears. So yeah, I'm always, you know, I'm always kind of concerned that I'm not so aware of the literature, but yeah. Well, there are some works here. Okay, geometrical. Yeah. Some things have been done. Okay, I can't. For now, they haven't been as successful as for me to get into them, but I can see here like there are some people who have thought about it. Yeah, as I said yesterday, somehow you can go almost everywhere where you went with complex and symplectic, and then the thing is some directions are successful and some others are just okay, you are doing math, yeah, you may publish papers, yes, but you really have to be quite in this field. You have to have a very high sense of aesthetics and say in a mathematical way, okay, either it's helpful, either it's beautiful, not just to be there just generalizing the world. Okay, we should try to generalize the things that are interesting. So
okay,
I can see something done. I don't know it, and I don't think it's what is done is like a great leap, I would say. Okay, but it is just my personal view, limited view.
Okay.
Okay, so if there are no other questions, let us thank Roberto again for his very nice mini course. Thank you very much.
Okay, thank you very much.